Now for a more advanced exercise, as you can see here, we are taking a closer look at the general dihedral group. So we take a regular n-gon, and n can be any natural number which is bigger than or equal to 3, and dn mat is the corresponding matrix group. So here, for example, you have for n equals 5, the regular 5-gon, pentagon, yeah. And here for n equals 6, the regular 6-gon or hexagon. And this time we choose the orthogonal canonical basis of R2, not as we did for the dihedral group in the video, where we adapted the basis vectors to the symmetries of the n-gon, but here we always take here this orthogonal or orthonormal basis of R2. So, as always, R denotes the rotation by 360 degrees over n, or 2 pi over n, and S is the reflection about the x1 axis. And if I draw the n-gons like that, this is always a symmetry. Yeah. Convince yourself here, if you reflect this n-gon, this pentagon here about this axis, you end up with the same pentagon, and exactly the same here for the hexagon. First of all, you need to explain why the cardinality of this set is 2n, so why there are exactly 2n symmetries of the regular n-gon. And actually in some books you might find the notation d2n instead of dn. I find this rather confusing because, yeah, dn is the symmetry group of the regular n-gon, not the 2n-gon. But that's the reason behind it. And then you're supposed to show that this group can actually be written like that. So R and S, these matrices, are the generators, because all these products of the powers of R and S give me all the elements in this group. And one inclusion here, we have to show the equality of these sets. One inclusion is easy, the other one is not so easy, so there is a hint here or instruction if you need it. And for that you need a pretty solid background in linear algebra, otherwise this is too hard. If you don't have that, you can actually show pretty easily that here these products, R to the k times S to the L, give you exactly 2n different matrices. And since this set here also has 2n elements, equality follows. This would be, I think, an easier approach, but this here has some nice arguments that I would like to show you today. All right, so I use a semi-geometrical argument. I think this should be okay in this context, since we are dealing with a geometric object. Here the regular pentagon. So if I have a symmetry, then vertex 1 gets mapped to any of these. So I have n possible choices or places where vertex 1 can go. And now comes the important observation: vertex 2 must stay a direct neighbor of vertex 1, because otherwise the symmetry would cut this line here. This is not allowed. Yeah, you're not allowed to cut and then rearrange this pentagon here, but the symmetry cannot destroy the object here. So, for example, if vertex 1 stays where it is, this is of course a possibility, then there are only two possible choices for vertex 2, namely here or here. In the first situation, I have the identity, because now the rest of the vertices, I have no more choice for them. Yeah, they must lie like that. If this here is the choice for vertex 2, then I have the reflection about the x1 axis, and again all the other vertices there's no more choice for them. By choosing the places where these two go to, the rest are uniquely determined. Otherwise, again, I would cut somehow or destroy my regular n-gon. And this is already the argument. By these two choices, the position of the new n-gon is already determined, and this is also important, every such placement of those two gives actually rise to a different symmetry. You can convince yourself, like in this case, that you will actually find 10 different symmetries by choosing here 5 possible places and then putting vertex 2 as a direct neighbor to vertex 1. Please try it, and you will find that those are 10 different symmetries of the 5-gon or pentagon, and there can be no more, as explained here. So this means the cardinality of this set here is n times 2, because I have here n choices and here only 2 possible choices, giving me 2n possible symmetries of the regular n-gon. Okay, now for the interesting part, or the more advanced part of this exercise. We take this set here and abbreviate it by capital M. So all the products of the different powers of matrix R and matrix S. For S we only need 0 and 1 as exponents because S squared is the identity, and so if L is 2 or bigger, then I repeat myself. The same here, R to the n is the identity, so it suffices that k runs through 0 to n minus 1. And we have to show that this set here, M, is actually the complete symmetry group of the, and we have to show that this set M is actually the complete symmetry group of the regular n-gon. So to prove equality of two sets, it is often convenient to prove that this set is a subset of this here, and the other way around, that this set is a subset of this. And then the only possibility is that they are equal. Now this inclusion here, that the set M is a subset of the symmetry group, is easy. Why have I written 4 always? Okay, so by mistake I always put a 4 down there, it needs to be an n. So this inclusion here is easy because by definition the matrices R and S belong to this set. Well, they are matrices of symmetries of the regular n-gon. And this is not just a set, but it is a group. Prove exactly as in the exercises before, or exercise number 1. So, if I take such a product, r to the k can be written as r times r times r and so on, or maybe r to the 1 or r to the 0, but then it's just the identity. And here s can be s to the l can be either the identity, which I can omit, or s itself. But now, since R is an element of this group, so is R times R, because a group is closed under multiplication. And then R times R is an element of this group, and so on. So this element times S is again an element of this group. So all these guys lie definitely in this set here. This is the easy inclusion. Now for the harder inclusion, this way around, we have to show that every matrix that belongs, again, here the n and here as well, every matrix that lies in this set here needs to be of this form. That means for every matrix here, we have to find natural numbers, including 0, k and l, such that A can be written as r to the k times s to the l. Actually, L01 is enough, and k runs between or from 0 to n minus 1, but that doesn't really matter here. So this is harder because we have to actually show how we come from this element here to k and l. Okay, now we are following the hint in the exercise. And I think it is enough if I explain you the basic ideas or the general ideas in the case n equals 5. And then it's not so hard to generalize this to any n. So we take a look at the regular pentagon. We have this basis vector E1, and we apply this symmetry matrix of the n-gon to this vector. Then, of course, we end up with a vector that points to any of these vertices, because after all, we have a symmetry of the regular pentagon. So I make another assumption to make it more concrete. For example, E1 gets mapped to this vector v, which points to vertex number 3. Again, it is easy to generalize. This can be any other vector. But I think the idea becomes clearer if we take this example proof here. So if A times E1 is this vector, I can rotate it here until I end up with the vector I started with E1. This is what is written down here. And in this case, I need to rotate it by 1, 2, 3 times alpha, where alpha is 360 degrees divided by 5, because we have n equals 5, so 72 degrees. So if I rotate this by 72 degrees, I'm here. Another 72 degrees, I'm here. And another 72 degrees, I'm at my original vector E1. And this obviously can be done no matter where this vector here points. So we will always find a rotation matrix, in this case r to the power of 3, because I apply r 3 times. And this applied to this vector here gives me E1. All right? Again, it's easy to generalize to any vector AE1. So this means the matrix here, this matrix, must have as a first column 1, 0, because here I end up with E1, which is 1 times E1 plus 0 times E2. If you're familiar with the notion of eigenvector, this means nothing but that E1 is an eigenvector to the eigenvalue 1 of this matrix. And the second column here, we do not know yet which numbers are in there. But we do know that this here is a matrix that corresponds to a symmetry of the regular n-gon, because A is 1 and r to the third power is 1, so their product is again. So it must be an orthogonal matrix, because symmetries must preserve length and angles, otherwise they could not be symmetries of the n-gon, and this is exactly what orthogonal matrices do. And now it's important that we have chosen this basis, E1, E2, they form an ONB, orthonormal basis, because they are orthogonal, obviously, and they both have length 1, so they are normed. So they are an orthonormal basis. And then the columns of an orthogonal matrix in this basis here must also be vectors that are orthogonal and have length 1. But then only 2 choices are left for this column here, namely 0, 1, which is orthogonal to that guy and has length 1, or 0, minus 1, which is orthogonal to this vector and has length 1. Those are the only choices that are left. And now we are almost done, because in this case I end up with this relation here. R to the third power times A is this matrix, which is nothing but the identity. Or in the second case, this guy here is this matrix, which is nothing but the matrix corresponding to the reflection about axis 1, which I abbreviate by S here. And then it's all about finding what A is, what A looks like. I multiply from the left with the inverse of this guy here, which is possible since I'm in a group. So I end up with A equals the inverse of r to the third power times the identity. But what is the inverse of r to the third power? This is simply r squared, because if I rotate here, r to the third power gives me this vertex here. If I rotate by another 2 alphas, 72 degrees, I end up at the origin. So the inverse of this is r squared. So in the first case, A is of the form r squared, which is exactly what we wanted. We have found k is 2 and L is 0. So I could put S0, s to the 0th power here. In the second case, I again multiply by the inverse to obtain A. So A is this here, the inverse times S, and again this is just r squared, so I end up with r squared s to the first power, which again is of this form here. And that's it. That's what we wanted to show. And as I said before, I think this gives you very clearly the basic idea of this proof. Now it's a good exercise for yourself to generalize this to arbitrary n. So you cannot argue here with 3 and 2 equals 5, but you have to write it down a little bit more involved. And to any r to the m, not necessarily here. R to the third a gives you this here as eigenvector, but r to the m. M can be any number. And do not forget the case m equals 0. And write down the proof, if you wish. Would be a good exercise, I think, but I am not going to do that. Then, alternatively, without all this matrix theory, you could simply show that here this set contains 2n elements. Then we know it is a subset of this set here. Again, here must be an n. And this already has 2n elements, so this leaves no choice but being equal. So these sets are actually equal. So we start with these powers here, and they are clearly different matrices. Either you write them down, if you know about rotation matrices, or more elegantly, you know the geometric background. These correspond to rotations by different angles, namely k times 2 pi over n. So they clearly have to be different matrices. The same for these guys here, all those multiplied by an s, because if those two here would be equal, I multiply from the right with s, and because s squared is the identity, this leaves me with r to the k equals r to the l, and this leaves me no choice but that k must have been equal to l. K and L always numbers between 0 and n minus 1. As we said here, this cannot be true unless those two are the same. So those are n different matrices belonging to the set M. Those are n different matrices, but they could be equal to those here. So this is the last point I have to check. It is not possible that any of those is equal to any of those here. We should put L here. Because if you know about determinants, you know that the determinant of such a matrix is nothing but the determinant of r to the kth power. The determinant is multiplicative, but the determinant of the rotation matrix is 1. So we have 1 to the k, which is 1. Whereas here I get, again by multiplicativity of the determinant of this guy times the determinant of s. This again is 1, and the determinant of s, no matter what s actually is, as long as it is a reflection, is always minus 1. So the determinants are different, so those cannot be the same matrices. This would be would call it pedestrian approach to show that those are equal. You don't need any or much background in matrix theory, but I think here there's some really nice geometric arguments combined with arguments from linear algebra, so I think this is a pretty nice proof. Alright, that it is for week number 3 or lesson number 3. I hope those solutions helped you. If so, please like, comment and subscribe, and I hopefully see you again next week. Bye bye.